So today, our last class of the semester, I want to just bring things to your mind, bring things to your memory by summarizing the entire course. Summarize the topics in our abstract algebra course. I think it's a worthwhile thing to do just to remind you of stuff, right? Try to bring things back to memory that are stuck in your memory somewhere deep in the recesses of your mind. And I will try to do it as much as I can from memory myself. And I will try to refer to particular chapters in Gallien's book, starting with chapter 0, Preliminaries. It is a pretty fundamental chapter. It's not explicitly about groups, rings, and fields, though there are examples of groups in that chapter. We started with just the basics of number theory. For example, GCD, greatest common divisor, sometimes also called GCF, or greatest common factor of two numbers. What does it mean to be relatively prime? You can think in terms of relatively prime in terms of two approaches. You could say you get two positive integers are relatively prime if and only if they have no common prime factors. That's one way to think of it. Another way to think of it is their GCD equals 1. And actually, a third way to think of it in relationship to the GCD as a linear combination theorem is that two positive integers are relatively prime if and only if there's some integer linear combination of them that equals 1, right? GCD of A and B equals 1 if and only if there exists integers S and T, one of which will have to be negative, such that AS plus BT equals 1. Effectively, an integer linear combination of A and B equaling 1. And yeah, one of those S or T would have to be negative to make this work. That's a fundamental fact to know as well. We also have the division algorithm in there, which of course says that given any two integers, A and B, where say A or where B is positive, and you're imagining dividing A by B, there exist unique integers Q and R such that A equals B times Q plus R, where this uniqueness, you should remember, is under the condition that R is greater than or equal to 0 and less than what you're dividing by, less than the B. The uniqueness, again, that backwards E means there exists, and the exclamation point here means unique. It's not a factorial. It exists unique integers Q and R so that this is true, where I'm implicitly assuming A and B are given integers and B is positive. So I'm taking an arbitrary integer A and dividing it by B. It's the thing I'm imagining doing. I get a quotient and a remainder. And we've seen that this generalizes to polynomials. That's what we've been doing recently. Also in chapter 0, we had some other fundamental things. We had, well, in number theory, we still had also modular arithmetic. We've done plenty of that during the semester. We also had equivalence relations and partitions. By the way, anytime you feel like you want to ask me a question, please let me know here. Right, with equivalence relations, it generalizes the idea of equality. And for example, congruence mod phi, for example, is an example of an equivalence relation. When you've got two integers whose difference is a multiple of 5, they would be a congruent mod 5. That's an example of an equivalence relation. They have to satisfy 3 properties: their reflexive property, symmetric property, and transitive property. And it's fortunate that those go in alphabetical order. Very nice: reflexive, symmetric, transitive. Reflexive is that A is always equivalent to itself for any A in the set. Symmetric is that if A is equivalent to B, then B is equivalent to A. And transitive is if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Every equivalence relation defines a partition of the given set, and vice versa. Any given partition defines an equivalence relation. And when you think about the partitions, there's your set here that you are thinking about defining an equivalence relation on. Any equivalence relation will generate a partition into what are called equivalence classes. These equivalence classes have no overlap. The intersection of any two of them is the empty set, and the union of all of them is the entire set S. We applied this idea with modular arithmetic. We also applied it with, for example, factor groups and factor rings. Cosets are equivalence classes for a certain equivalence relation. I'll remind you of what that is when we get to talking about factor rings and factor groups and factor rings. And stop me if you got a question at all, if you want me to expand on anything. I know I'm going to go quick here. I'm going to try to cover pretty much everything. We also talked about functions in chapter 0. Facts about functions, definition of one-to-one and onto. And when they are one-to-one and onto, they have inverse functions and fundamental properties that those satisfies related to function composition. Chapters 1 and 2, all grouped together, get into the basics of group theory. Chapter 1 is a very intuitive introduction, thinking about a particular example. The example that the book discusses is the symmetries of a square. A fundamental kind of example to be comfortable with. Corresponds to the dihedral group D4. Right, dihedral group. The 4 corresponds to the fact that these are symmetries of a square. The number of elements in the group, though, remember, is 2 times 4, 8. This is of order 2 times 4 is 8 because you have 4 rotations and 4 reflections. Though one of the rotations is the identity mapping, which is, you might argue, is not really a rotation because you're not actually doing anything. We labeled the elements R0, R90, R180, R270. Those are the rotations. Then the reflections are labeled H, V, D, and D prime. You know, basic things about this group is, well, for one thing, it's not cyclic and it's not abelian. This is an example of a non-cyclic, non-abelian group. There is a smaller example of such a group. What's a smaller example of a non-cyclic and non-abelian group? I'm thinking of one that has order 6. I'm thinking something smaller. D3, symmetries of a triangle, equilateral triangle, which is also isomorphic to S3, the symmetric group on 3 objects. Those 2 groups have 6 elements and they're isomorphic to each other. And they're non-abelian and also non-cyclic. Remember, all cyclic groups are abelian. There are some abelian groups that are not cyclic. We'll come back to that. So there's an example there. That's what the group is as a set, in terms of the operation, it's function composition. You know, before this class, technically speaking, well, you may have had a class where you used a little circle for function composition. But here we just juxtapose, we just put these things next to each other and it's assumed you know to do function composition. Then in chapter 2, we get a bit more formal, the definition of a group. So fundamental to the course. You might say, I can't resist putting that on the final exam. So fundamental, right? Is that a big hint? Definition of a group. I hope it's familiar enough that it seems like it's not a problem. Some other fundamental definitions. More definitions. Well, okay. Basic facts about groups. What do I mean by basic facts? I mean things like rules of exponents, for example. A to the n times a to the m is a to the n plus m. It's not part of the definition, so technically you should be able to prove it. Proving that this is not so pleasant, actually. If you're going to try to prove it in general, you'd have to sort of consider a couple of cases probably, and in each case, think about induction. So it'd be not so pleasant. I probably wouldn't be putting such a proof on the exam. I guess it wasn't on an old exam anyway, right? And it's how I'm constructing the final exams. I guess yours would not have that. Other basic facts include uniqueness of the identity, uniqueness of inverses, right? They're not part of the definition of a group, so you technically have to prove them. There's the socks shoes property for inverting A times B. You do it as B inverse times A inverse in the opposite order. There's the definition of an abelian group. Okay, those are the examples of the basic facts and definitions that I'm thinking of. It's possible I'm missing something from chapter 2 here, but I think we better move on to chapter 3 anyway. Chapter 3 is about subgroups. Let me lump chapters 3 and 4 together, actually. Chapters 3 and 4. You could say, well, you could say subgroups, order, and cyclic groups are the main topics of chapters 3 and 4. So I think we start off in chapter 3 with a definition of, I'm not sure if it's the first thing or not, the definition of a subgroup. You got a group G, you got a subset H. What does it mean for H to be a subgroup of G, notated like this right there? That looks like a less than or equal to sign. It's not really in this context, though it's a similar kind of, somewhat similar kind of meaning, in that H is smaller than or equal to G. H has to be a group itself under the same operation of G. You don't change the operation. If you create a subset of it, G, and you define a different operation, it's technically not a subgroup because it's a different operation. So that's got to be part of your description of the definition. Then we got the subgroup tests, the one-step subgroup test, the two-step subgroup test, which can always be used. You can always use those. There's also the finite subgroup test, which can only be used when you've got a finite group. For the finite subgroup test, all you have to verify is closure of H. With the one-step subgroup test, it's not really one step. Well, okay, even with the finite subgroup test, you also have to verify non-emptiness. In all these tests, the 0th step, you might say, is confirm that H is non-empty. And the usual way to do that is confirm the identity E is in H by however H is defined. Yeah, with the finite one, after that point, just verify closure. With the one-step subgroup test, assume A and B are in H and show A, B inverse is in H. Remember that? With the two-step, you have to do 2 steps. So you might think it's a little harder, but it's conceptually, it's a little easier. That's why we go ahead and have a 2-step subgroup test. You verify closure. If A and B are in H, then A times B is in H. And you verify closure under inverses. If A is in H, then A inverse is in H. And sometimes it's just easier to use the 2-step subgroup test. In fact, that's usually what people prefer using. Examples of subgroups include, our main example was the 2 examples was the center of G, Z of G, and centralizer of an element. The center of G is the set of everything in G that commutes with everything else in G. Say that again. Tracking with me? The center of G is the set of elements in G that commutes with everything in G. In extreme cases, that might just be the identity element. In fact, I think with D3 isomorphic to S3, it's just the identity. Centralizer of an element A is the set of everything in G that commute with A. The center will be a subgroup of any centralizer. There's only one center, there's lots of centralizers. There's one centralizer for each A, though different A's could give you the same centralizer. If you commute with everything in G, you're going to commute with A. Another fact I emphasized, at least in the lectures, I don't remember if I emphasized it in here, was that the intersection of any collection of subgroups is a subgroup. I won't bother writing that down, but that's a fact. Got a bunch of subgroups, take their intersection, it will also be a subgroup. Not necessarily true about unions. We also had the definition of order of a subgroup. Definition of order of a subgroup, or you could say a group overall, and an element. Okay, I think order is defined just in terms of a group initially, not a subgroup necessarily. What's the order of a group? Let me go ahead and get rid of the word sub. Well, if the group has a finite number of elements, the number of elements is the order. If it has an infinite number of elements, then you just say the order is infinite. Do you write this equals infinity? In that case, yeah, it's okay to write. I'm not saying infinity is a number when I write that, though. It's just shorthand notation. The order of an element, this is always a little tricky. It's not the power that gives you the identity. That's not the definition. It's the smallest positive power that gives you the identity, if such a smallest positive power exists. Smallest, you got to make sure to put the word smallest in. Such a power may not exist. You may have an element with infinite order. But if there's a smallest positive power, positive meaning also non-zero, that gets you back to the identity, that's the order of the element. Done plenty of examples of that. Chapter 4 is about cyclic groups. First, what is the cyclic group generated by an element in any group, cyclic or not? It's the set of all powers of that element. That's what the cyclic subgroup generated by an element is. You can always do such a thing no matter what your group is. Cyclic or not, abelian or not, doesn't matter. Right? You can always generate cyclic subgroups. The entire group is cyclic only when it does equal a cyclic subgroup generated by an element. If that's true, then the entire group G is called a cyclic group. And as we've seen with examples, except in the most trivial case of a group with one element or two elements, you're going to have more than one generator. For example, Z4 is generated by 1. It's also generated by 3, not 2 or 0. The operation here is addition. So we're not talking about powers of these things. We're talking about adding them to themselves. Z5, for example, is generated by all the positive numbers in it. They're all generators, because all those numbers are relatively prime to 5. In general, Zn has Euler phi of n generators. And the generators end up being elements of un. Zn is our prototype cyclic group of order n. Elements are 0 through n minus 1. Operation is addition mod n. Un is not necessarily cyclic. It could be, but not necessarily. Depends on what n is. The elements of this are the positive integers less than n that are relatively prime to n under multiplication mod n. Relating this to ring theory, if you're thinking of Zn as being a ring, so the operations are addition mod n and multiplication mod n, then U of n really is its group of units. It's the elements in Zn that have multiplicative inverses. So all these things are related to each other. Make sense? Remember these things? It's good to try to bring these back to your memory. It's fundamental facts about cyclic groups in chapter 4. I don't have time to list them all out. Probably the most important, though, is the fundamental theorem of cyclic groups, FTCG. What does it say? You got a cyclic group of order n. I'm not going to write it out. For each divisor of n, there's exactly one subgroup of that order. It's in part a generalization of Lagrange's theorem, which we haven't gotten to yet. Or specialization of Lagrange's theorem might be a better way to say it, for cyclic groups. For each positive divisor of n, there's exactly one subgroup of that order in any cyclic group. And those subgroups themselves are cyclic. Remember that? Yeah, other facts in chapter 4, I don't have time to review them. That's right, again, we're trying to do a fast overall review here. Chapter 5, permutation groups. Our main example is Sn. Though you should realize there are other permutation groups. What's a permutation? A permutation is just a one-to-one and onto function from a set to itself. That's what a permutation is. The set could be infinite. Any one-to-one and onto function from any set to itself is a permutation by definition. A permutation group is a set of permutations of the same set that form a group under function composition. Our main prototype, again, is Sn, where the set is the collection of numbers 1 through n. The numbers 1 through n are not the elements of the group, right? They're just the set that those functions act on. And we write them in either array notation or mostly cycle notation. And there were very fundamental facts to know. Well, first, make sure you understand cycle notation. Secondly, things like disjoint cycles commute, that the order of a permutation, if it's written in disjoint cycle notation, is the LCM, least common multiple, of the orders or lengths of the individual cycles. If they're disjoint cycles, there's no common numbers in them. If you're confused, look at examples. We've done them before. There's the alternating group AN of even permutations. A permutation is even or odd, depending on how you can write it in terms of 2 cycles. the number of true cycles, whether it's an even or odd number. Sn has order n factorial. An, the alternating group, is a subgroup with order n factorial over 2. Chapter 6 is isomorphisms. Group of isomorphisms from a group, let's call it G1 to another group, G2. 1-to-1 and on to an operation preserver. Isomorphisms by definition from a group to another group are 1-to-1, onto, and OP. Operation preserving. In the abstract, you'd write that like this. Bunch of properties that isomorphisms satisfy. They preserve all group theoretic properties between G1 and G2. When there exists an isomorphism between G1 and G2, we think of G1 and G2 as being the same group up to isomorphism, if you want to add an extra phrase. So the order of G1 and G2 would have to be the same. The order of elements would have to match up. Elements that phi maps in G1. You got an element in G1. Phi of that element in G2 is going to have the same order as the original element in G1. Plenty of other properties that you've, I hope, become familiar enough with it that you don't even have to think about it much. There's also a discussion in this chapter about groups of automorphisms, aut G. Automorphism means isomorphism from a group to itself. Auto means self. So automorphisms are isomorphisms. I forgot to remind you, back up here, all cyclic groups are abelian, but not all abelian groups are cyclic. I haven't talked about external direct product yet, but there's an example of an abelian group that's not cyclic. That's the simplest example, in fact, of an abelian group that's not cyclic. Coming back down here again, all automorphisms are isomorphisms because they, by definition, they are isomorphisms from a group to itself. Not all isomorphisms are automorphisms. But this is a group under function composition. And then there's a subgroup of it, N of G, the group of inner automorphisms. Those are special automorphisms that have a special formula. I'll let you look that up. As an example, aut of Zn turned out to be isomorphic to Un. As an example of a special fact in chapter 6. Chapter 7 is really the hinge of group theory, Lagrange's theorem. It's the hinge or maybe foundation, whatever, however you want to picture it. Let's go ahead and write it. If G is finite and H is a subgroup of G, then the order of H divides the order of G. Moreover, the number of left cosets or right cosets of H in G is the order of G divided by the order of H, and that'll be a positive integer since the order of H divides the order of G. So chapter 7 is also about cosets. because cosets are a fundamental tool for proving Lagrange's theorem, first of all. And then in chapter 9, they also become a fundamental tool in terms of defining factor groups. Relating this to equivalence relations, one example of an important equivalence relation in this class is to say A and B are equivalent. They are elements of G. If and only if they can represent the same left coset, for example. There's also an equivalence relation involving right cosets, which could be a different equivalence relation in general than the left coset definition. And this is also equivalent to A inverse B being in H, which is also equivalent to B inverse A being in H. But make sure the inverse symbol is on the element on the left when you're talking left cosets. That's an example of an equivalence relation, and the equivalence classes are the cosets themselves. Probably our most important example of an equivalence relation, besides modular arithmetic, congruence mod n. In this chapter, we also have the, as an application of Lagrange's theorem, the orbit stabilizer theorem, which I did test you on exam 2. So it could be on the final exam. There was an example of computing orbits and stabilizers, and then there was a problem about stating the orbit stabilizer theorem. I didn't have you prove it. It is, if you look at the proof, an application of Lagrange's theorem. It's not something I emphasized in class, but it was in the lectures. And I want you to watch the lectures too. But as far as studying for the final exam, just make sure you work on remembering what is a stabilizer, what is an orbit, and what does the orbit stabilizer theorem say, and be able to illustrate it with examples. Orbit stabilizer theorem, if you're interested, has some pretty neat applications itself. There is an application to a symmetry group in 3 dimensions, like of some sort of 3-dimensional solid in the book as well. Chapter 8 was about external direct products. In general, maybe you've got something like this. Written that way, the elements are ordered pairs if you've got 2 groups that are being combined, ordered triples if it's 3, or you'd call this an ordered n tuple if there's n of them. And the group operation is component wise. You'd call these things components or coordinates. Component wise. So that's the definition of an external direct product. You've got the LCM condition about the order of such an element, assuming each of these components has finite order. So this equation I'm writing only works when all these are finite numbers, right? Can't be infinity. There's also various isomorphism facts in chapter 8. For example, Zm external direct product with Zn is isomorphic, is cyclic, you might say, to this, if and only if the GCD of M and N is 1, if and only if M and N are relatively prime. You've got information about UN group, isomorphism classes, isomorphism facts, isomorphism. For example, U10, for example. Let's do a little bit more interesting example. U15, since 3 and 5 are relatively prime, turns out to be isomorphic to the external direct product of U3 and U5. And then both of those things, since 3 and 5 are prime, are cyclic. This one's isomorphic to Z2, and this one's isomorphic to Z4, for example. Chapter 9, normal subgroups and factor groups. Our book calls them factor groups. Plenty of other books call them quotient groups. So there's the definition of a normal subgroup. H is normal in G, written that way, if and only if every left coset is equal to the corresponding right coset. A capital H equals capital HA for all A in G. That doesn't imply G is abelian. This is not necessarily implying G is abelian. We're not necessarily saying A times a little h in capital H equals that little h times A. They don't necessarily commute. As sets, these are equal. So that's the definition. There's also the normal subgroup test. Which for the sake of time, I'll just let you look up. There's the definition of a factor group. And the key thing is that H needs to be normal in G to define the factor group in the first place. It's typically thought of in terms of left cosets, though technically you could think of it in terms of right cosets. The elements of the factor group are cosets. Left coset. And the group operation in the factor group is done by multiplying the representatives, right? A times H, AH times BH equals ABH. And what was the key thing that we end up proving to, that you need the normality of H to prove this is going to be a group? Do you remember what I called it? It starts with a W. It's a two-word thing, WD. The normality makes the operation well-defined. That's the key thing. It doesn't depend on the coset representatives. There were also various other facts in chapter 9, including the GZ theorem, classification of certain groups, of certain finite groups. Not a complete classification theorem or theorems. Partial, including classification for groups of order 2p where p is prime. I think we also had a classification. Let's see. Well, in this case, G is either cyclic or isomorphic to dp. Was one example of a classification theorem we had. There was a theorem also about identifying the isomorphism class of the group of inner automorphisms. For sake of time, let's move on to chapter 10. Need to go faster here even. Chapter 10 was about homomorphisms. And the big theorem in that was actually called the first isomorphism theorem. Homomorphisms are operation preserving, but they're not necessarily one-to-one or onto. First isomorphism theorem, when you got a homomorphism from G1 to G2, then the factor group of G1 by the kernel of phi is isomorphic to the direct image of G1 under phi. And if phi is onto, then it means it's isomorphic to G2. So you also define the kernel in here, and you show the kernel is a normal subgroup. So you can consider this factor group. So the big thing is the first isomorphism theorem and its applications. Chapter 11 was about classifying finite abelian groups. They are isomorphic in general to either cyclic groups or external direct products of cyclic groups. And we could try to figure out, based on the order of the finite abelian group, the different possible isomorphism classes. That's where we talked about the partitions of the powers of the primes and the prime factorization. If the order of G, for example, is 2 to the 4th times 3 to the 3rd, you need to think about the number of partitions of 4. How can you obtain 4 as a sum of positive integers? And number of partitions of 3 to figure out the number of possible abelian groups of this order. The partitions of 4 are 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. And we don't think about reordering these with a commutative property to get a different partition. Partitions of 3 are 3, 2 plus 1, and 1 plus 1 plus 1. So there's 5 partitions of 4. There's 3 partitions of 3. Altogether, you'd have 5 times 3, 15 possible abelian groups of order equal to this, whatever that number is. 16 times 27, whatever that is. Chapter 12 started ring theory. Chapters 12 and 13 are the basics of ring theory. Ring theory fundamentals. So definition of a ring. It also, you find in these chapters, definition of an integral domain and a field. We didn't do more advanced field theory until recent weeks, but we had the definition of a field way back in chapter 13. Integral domains, you need the definition of a zero divisor first. You don't want integral domains to have zero divisors. Field, think of the definition quick here. It's a commutative ring with unity in which every non-zero element is a unit, has a multiplicative inverse. Commutative ring with unity, a 1, in which every non-zero element has a multiplicative inverse. Every non-zero element is a unit. Every field is an integral domain. There are no zero divisors. Basic facts about rings. For example, something we emphasized in class was that proving that 0 times A equals 0 for all A in the ring. That's not part of the definition of the ring. We had to prove that, for example. Some other things included that every finite integral domain is a field, that Zn is a field if and only if n is prime. Definition of the characteristic of a ring. Chapters 14 and 15 kind of get lumped together as well. About ideals, factor rings, ring homomorphisms, and a first isomorphism theorem for rings. But there are also important definitions of a prime ideal and a maximal ideal, though we've mostly focused on maximal ideals. And the fundamental fact here that if R is a commutative ring with unity, then R mod A is a field if and only if A is maximal in R. There are also important things related to factor ring calculations, being able to just compute products of cosets in a factor ring, and the property. That's the definition of an ideal that gets used when you do those calculations. There are a bunch of other facts, and I'm thinking especially in chapter 15, we didn't really have time for. More at the end of chapter 15. And I don't think I emphasized on the exams. Chapters 16 and 17 kind of go together. Polynomial rings. Rx, where R is a commutative ring. And Fx, say, where F is a field, especially we focused on this kind. Well, remember, I really emphasized a lot, even when F is a field, this thing is not a field. Its only units, in fact, are the non-zero constant polynomials. There's a division algorithm in Fx. And there are things like the remainder theorem and factor theorem. Remainder and factor theorem. The factor theorem being a bit more familiar, saying A is in F is a 0 of a polynomial little f of x, if and only if x minus A is a factor of f of x. Being able to do long division or synthetic division with ordinary numbers or modular arithmetic. Only use synthetic division when you're dividing by linear polynomials, say x minus A, which means you put just A itself on the left in the synthetic division. Chapter 17 is all the irreducibility tests. The ones we made the most use of included the degree 2 or 3 irreducibility test. Right? If your polynomial has degree 2 or 3, it's going to be irreducible over the field if and only if it doesn't have a 0 in the field, which also means it's reducible over the field if and only if it does have a 0 in the field. Once you get to degree 4, it gets harder. You have to either use Eisenstein if it's available, although that's Eisenstein's criterion only applies when you're talking about factorization over Q. And it's very specialized. The coefficients have to be related to a prime in the way that you learned about More generally, you might hope the mod P irreducibility test applies. And hopefully when P is just 2 or 3, so it's simpler. Though I did mention it doesn't always apply. And the main important examples where you can't apply it, actually, the main important example is x to the 4th plus 1 is our main important example where you can't apply the degree 2 or 3, and you also can't apply, at least not directly, the mod P irreducibility test. This does end up being irreducible over Q, as we've talked about recently even. But none of those tests are enough to prove it. You need some other technique. Learning how to factor it in terms of complex numbers is the main technique. It is reducible over R. You can factor this, we saw even on Wednesday, I think, as a product of 2 trinomials where the middle term involves square root of 2. So it is reducible over R, but not over Q. Chapter 18 was general divisibility, theory in integral domains. So that included definitions of, in a general integral domain, what does it mean for an element to be prime? What does it mean for it to be irreducible? And they're different. One's related to units, and one's related to a generalization of Euclid's lemma, which I forgot to mention back in chapter 0. You should know Euclid's lemma. If a prime divides A times B, then it's either going to divide A or B. And then there were other things in this chapter that were a challenge. There was the idea of a norm, and using that, there was a relationship between irreducibility and prime. And there's also the idea of unique factorization domains and Euclidean domains. It was all pretty technical, pretty difficult. We didn't have a ton of time. And I think what I tested you on mostly for exam 3 was just factual information, which is probably what I'd keep it to for final exam here, since that's what I tested you on with exam 3. You know, when you haven't worked with it much, it's hard to remember those factual things, and you might say it's sort of maybe worthless since you didn't work with it much. But it was on the exam, so it's something you should look at again and think about at least for 20 minutes or something. Then, okay, chapters 19 through 21 and chapter 30 is the recent stuff. And this chapter 19 through 21 really also included the old edition's chapter 19, which was about vector spaces. So this is what I made the video about yesterday and posted this morning. Vector spaces, I'm not going to write it down here. Vector spaces, linear independence, basis, dimension. Field extensions, splitting fields, theorems about simple extensions, our theorem being 19.3. That one probably being our favorite one, especially the second part of it. Relating this to vector spaces as well, and the fact that any field will be a vector space over a subfield. If the subfield is the coefficients, the C's in this case, any field's going to be a vector space over a subfield. Question?
When you say there was stuff chapter 19, is that chapter 19 this book or the whole?
Both.
Okay.
The old edition chapter 19 is the vector space stuff that I handed out to you. The new chapter 19 used to be chapter 20 in the old edition, extension fields. The fact that you can uniquely express the elements this way is enough to say these elements, these powers of A, are linearly independent as well as that they span. And this means, based on P of X being irreducible with degree n, that F of A, the field extension there, is an n-dimensional vector space over F. And that is also called the order of the field extension. And since it's a finite number in chapter 22 or 20, that also means it's what's called a finite extension. This definition. E has degree n over F, and we write that if E has dimension n as a vector space over F. If that dimension is finite, E is called a finite extension. It doesn't mean E is a finite set. And it doesn't mean E is obtained from F by adding just a finite number of elements. It means exactly what it says here. The dimension of E as a vector space over F is finite. There's a finite basis. Otherwise, you say it's an infinite extension. All finite extensions are algebraic extensions. If the dimension of E as a vector space over F is finite, if there's a finite basis, then all the elements of E will be algebraic over F, meaning they will be zeros of some polynomial with coefficients in F. That's the definition of algebraic. There's this fact, which I really haven't had time to emphasize, that does come up on some practice problems. It's something you should know. It's kind of a generalization. You might say it's a field theory version of Lagrange's theorem from group theory. It's information about multiplying, in this case, degrees of field extensions when they are finite. We mostly consider lots of examples as we're considering these topics. And we're always hoping for our examples that we could write the extensions as what are called simple extensions. And this theorem guarantees you can when the field has characteristic 0 and when the elements A and B are algebraic. You can find a C where that's true. And this was one of the main examples we talked about. And in fact, in yesterday's video, I did an example like this, and that was one of the problems. That was the problem in yesterday's video that's most like a proof. I phrase it as explain, but in a sense, you could call it a proof. Proving that this kind of thing equals that kind of thing, except I did a different example. And so you need to understand these symbols. Remember these field adjoin elements. You have to understand what the symbols mean. And that was a very important definition. I think I can't resist putting that definition on your final exam. Is a big hint. Definition of the symbol F adjoin. It's not really even listed as a definition in the book. It's described here, but it really is a definition of what this symbol means. Smallest subfield of E containing F and containing all these A's. 367. It's by the definition of a splitting field. It does not mean that this thing represents the union of F and just those A's. It's going to contain much more. We drew pictures for this where I drew the dots and then surrounded the dots. Very important definition, even though it's not listed as an official definition in the book. And we had facts about finite fields and Galois theory. 3 minutes for Galois theory. Ha ha ha. Okay, I do have more time for Galois theory in the lectures, right? So you should watch the lectures. If you haven't, you need to catch up. We did talk about on Wednesday the definition of a Galois group and a fixed field. Let's just spend, okay, we're down to 2 minutes. I'm still paging through it. Fundamental theorem of Galois theory. Oh, I can't describe that in 2 minutes for sure. All I can do is hint about it. Yikes. Now, here's a complicated example of it. It's as a theorem statement, it's a technical way of describing exactly what's going on and relating the lattice diagrams here, one for the Galois group and its subgroups, and one for the field extension and its subfields. Simpler version would be like this one here. I think I do talk about this one in the lectures. So the field extension we're talking about here is this field extension of Q. Q adjoin root 3 and root 5. And an example of a question you might want to answer using Galois theory here is, what are the subfields of this field that are also field extensions of Q? This lattice diagram gives the answer, but how do you figure that out? You got to use the fundamental theorem of Galois theory. You got to come up with the Galois group of this field over this one and figure out its subgroups. And the theorem is essentially saying there's a correspondence between these lattice diagrams. And for example, that would mean since there are, well, if you include the trivial subgroup and the whole group itself, there are 5 subgroups of the Galois group, there's got to be 5 fields in this diagram too. And the ones that are in the middle correspond to fixed fields of these subgroups. Read details of the example to help you understand how that all works out. The numbers over here correspond to indices of the subgroups in the bigger group. The numbers over here correspond to degrees of the field extensions. And those numbers match. Should also know, though you don't have to study it, that in chapter 30 on Galois theory, it is proved at the very end. It's just a fact to know, there is a quintic that's not solvable by radicals. As a historical fact to know, as the motivation for Galois theory in the first place. Now, Galois lived 200 years ago. There's no way that Galois himself created all of Galois theory, right? The definition of a group had not even been created then. I'm serious. Galois was working with groups before he knew they were groups. I think he maybe did use that word. So historically, it didn't look, Galois didn't look like what's in the book, but that's what was really going on in the end. So I hope by bringing things to your mind, it was still worthwhile. The video itself goes into details, and you should try to, as you go through the video and pick and choose perhaps, you should think about trying to recall definitions and facts and try to do calculations before you see what I do, because that'll be the more beneficial way to do it. See you next Monday.